x approaches 1. So on your graph here's x equals 1 right here on your graph, and you're supposed to sort of trace from the left and then from the right, and you want to know where this point is. So the limit is always a y value, and the y value is whatever that y value that it approaches. Now it's a hole right there. The hole is okay. Limits just have to be the thing that you're approaching, not the actual value there. So it approaches this y value of 7. Here, let me just double check. 1, 2, 3, 4, 5, 6, 7. Yeah. And then the other problem asks for the limit. Let me snip this in. The part B, it wants the limit as x approaches -1. Okay, sorry, that didn't really, where did that, sorry, we'll just put it down here. Okay, so for -1, limit as x approaches -1, you look at where -1 is, and you go to sort of that point, and then you approach it from the left and from the right, and what you hope is that it approaches the same value. And it does. In this case, it approaches positive 1, and it's a y value. It's the y value of the graph. Any follow-up to that one?
No. I'm just give me 1 sec on everything.
Sure.
Okay. All good.
Okay, so let's move on to question number 2. All right, so question number 2 says to construct a table and find the indicated limit. So there's quite a bit that's not implied there, that's implied here that you don't know, but you're supposed to be using the following formula: f of x plus h minus f of x over h, or a variant on that is f of b minus f of a over b minus a. Okay. But that's where we're going in terms of like what you're supposed to do here. You're supposed to take this value for x and put it into x in both places, and then they want you to round to 4 decimal places. And what you're supposed to see is a pattern as you do this. Okay, so it's we're going towards this on the top right, but for this problem we're just substituting those numbers in each time. All right, so I will do that. Let me think of the best way to do that here. I'm actually going to open up an Excel thing so that I can snip the results in pretty quickly here. Would you like me to share that Excel screen, or can I just go ahead and do the calculations?
Yeah, you can just do it.
Okay.
You wouldn't open up like Desmos or anything to do that?
So you could, yeah, actually that's better. Let me do it that, because that does give us the repeatability that we're looking for. So let me do that. Desmos Scientific. All right. So new share. All right. So it's slightly programming, but really it isn't. So I'm going to go x equals 8.9, and I'm going to hit enter, and that stores at 8.9 into x. And then in the next line here, I can actually do square root of x plus 2 over x minus 9, and you can see that it gives you the value over here on the right.
Okay. And
what's nice about this, and I'll write these in, but it won't be as organized. It'd be better if you could grab them as we go. 49.8329. What's nice about this one is when I change to 8.99, the calculation automatically adjusts here. I'm sorry, this is not quite right. I apologize. There's I guess they are doing this difference quotient. So because this number just got way too big. Okay.
Okay.
We actually do a little bit more here to it. So so each time we're dividing this by x minus 9. No. I'm just trying to decide how to get us to do this so we can repeat it each time. Why? No, it's let me just keep going here.
Okay.
Okay, I see. All right, no, this is okay. I'm sorry. This is okay. I
Sure.
wasn't expecting what it's actually. So the second box you would fill in with minus 499.8 or 0.8333, and then we do this again, and it's actually okay that the numbers are getting bigger. So the next number would be minus 4999.83333. And then we switch to the other direction. So we go 9.001. Okay. And at first you're thinking, why did it switch signs? Now it's 5,000.1667. And then the next box, if we go 0, 1, obviously it's gonna be a little bit smaller, 500.166. And then 9.1, get our last value, there's 50.1662. So let me go to the graphing calculators because that's going to be make more sense here when we graph this. So square root of x plus 2 over x minus 9. And what you're going to see here at 9 is that in one direction it goes down and then the other direction it goes up. And I was initially thinking it would go to a point because I wasn't really thinking very clearly about this problem, but that's why the numbers get so small negative and so small positive, is because there's a vertical asymptote at 9.
Okay.
So in terms of our question, let me go back to the other screen. In terms of what we're being asked to do, we're asked to determine the limit. Well, the problem is the graph, as I just mentioned, it goes down, it goes up, so the limit does not exist. I think that's even an option there to say that it's letter B. B would be the right one there, but you got to fill in these values in the table.
Sure. Okay. So negative 49.839.
Yeah. Now I might have messed up a decimal place somewhere in here, but these also redone.
And 50. Yes. Okay. All right. All good. Can you hear me, Matthew?
Yes, we can
Okay.
move to the next one here.
Mhm.
All right, so this question here is a more standard limit problem. So even if you don't know anything about calculus, you know enough to put -2 in for x. Okay, and that becomes -2 squared minus 4 over -2 plus 2, which is 4 minus 4 over 0, 0 over 0. And this is actually called indeterminate form. But for you, the issue is you just can't divide by 0. Okay, so you can use some algebra to simplify this thing in parentheses here. So in prior courses, there's this thing called difference of squares, which factors to a minus b, a plus b. In your problem, your a is x, or your little a is x, and your little b is 2. So it becomes x minus 2, x plus 2. And that's the numerator. So the numerator becomes x minus 2, x plus 2 over x plus 2. And you can actually cancel those.
Okay.
So that means it's the limit as x approaches minus 2 of x minus 2. And now you just put that number in again. You just try it again. And this time it works out. Minus 2 is minus 4. And that's your answer. So there's always an algebraic limit where you have to use some sort of factoring to be able to answer it.
So you did it like two different ways, right? Like you took
Well,
in the above, you took the -2 and you plugged it right in.
yeah, you try it, but it doesn't work because you can't divide by 0.
Yeah.
So then you manipulate the equation to hopefully make it into something that does work.
So, but is that always your first step, is to plug
Yes.
in the number first and see
Yes.
what comes?
Yes, and that's
Okay.
that's what I wanted you to understand out of this is you always try the number and you always go back to trying the number
Okay.
because sometimes it works.
Huh. Okay.
All right, so the next question here. All right, the next question here is kind of the same deal. Try find the limit. You'd put the number in for x, and you'll see that it's the square root of 121 minus 11 over 121 minus 121, 11 minus 11 in the top, over 0 on the bottom, 0 over 0 again. So that's bad. I mean,
Okay.
that's like what do we do? So I call it a non-obvious thing to do here because it really is. You just until someone tells you to do this, you'd have no idea that this is what you're actually supposed to do in the next step here. So you actually multiply the top and bottom by what's called the conjugate of the numerator. And the conjugate here just means that it's the same thing, but this sign is flipped or this operator is flipped.
Mhm.
Now in math, you can always multiply the top and bottom by the same thing. So that is an allowable thing to do. You FOIL the numerator. So let me just write the numerator off to the side here. So when you FOIL this, first times first, so square root of x times the square root of x is x. Square root of x times 11 is 11 square root of x. Minus 11 times the square root of x is minus 11 square root of x. Minus 11 times 11 is minus 121. These cancel, and you get x minus 121 on top. So in your numerator, it's x minus 121 over x minus 121 times square root of x plus 11. And you're really supposed to rewrite this limiting stuff down here each time. Now, again, you get a cancellation, which is what you want. That's what you're looking for here. So the numerator becomes 1 over square root of x plus 11. And then you just try the number again. And you can see that this time it works out. 1 over 22. So there are a couple of these types. So this is your final answer, by the way. There are a couple of these types of questions where you have to know the thing to do, which you wouldn't know until you've taken the class, to be able to manipulate the equation to get it down to where you can work it out again.
That's fun. I like that.
Yeah, it's it's different. So, okay, let's look at the next problem here. So limits are kind of the very first thing you learn as like actually part of calculus is limits or our limits. No, I don't want to link. Okay, so again, if you put 0 in, hopefully you can see that you get 0 on the bottom, and that's enough to just like stop. I mean, because you can't divide by 0, but in the numerator it becomes x plus 0 squared. The x squared minus the x squared cancel. So in the numerator, we're going to expand this x plus h squared. And as a reminder, since you haven't had math in a while, it's really good to write it out this way and then FOIL it again. So if x times x is x squared, x times h is xh, x times h is xh, h times h is h squared. And then you're subtracting this x squared, that's your numerator, over h. And what happens is all the terms that are left over, they have an h in them. So there's actually two xh's, there's two of them, plus h squared over h. And then division is sharing, so you have to share both of these. So it's really 2xh over h plus h squared over h. The h's cancel. This h on the bottom cancels with one of these. Now you have 1. And your final answer is 2x plus h.
Okay.
And that comes from just expanding the binomial x plus h.
Okay. So, but is that the answer, or because last time you plugged the previous number in, but obviously this is 0.
Oh, I'm sorry. Yeah, you're right. You do need to plug 0 in.
Oh,
I
okay.
didn't see that. So yeah, you got to put 0 in for h, so it just becomes 2x.
Okay.
Yes, plus 0, which is 2x. Yes, you always have to put that number back in.
Okay. Okay. Cool.
All right, next question. Okay, so this problem here, let me grab it. Most of calculus can be done with a graphing calculator, and when I say that, I mean by graphing things. And this is an example of that. If you were to graph this, this function here, and I ask you, well, what happens as x goes to infinity? You're just looking at, well, what happens way to the right side of the graph here? But there's, of course, also the calculus way that you're supposed to do this. And the calculus way here is to identify the largest power. So in this case, it's x squared. You look at the numerator and denominator, and then you divide everything by x squared. So I'm gonna need more room, so I'll show you that down here. You divide the numerator by x squared, and you divide the denominator by x squared. And again, it's the same idea as you can multiply or divide anything by the same thing. So if you can imagine dividing each of these in the numerator by x squared, actually, I might as well write that. And then similarly on the bottom, you divide everything by x squared, you're going to see a lot of cancellations. Okay, so it becomes 7 plus, and then this one on the right here is 2 divided by x. This is on the bottom here is 4, okay, minus 3 over x plus 1 over x squared, okay. And you know, in some ways you might say, well, hey, it doesn't look any better than where we started, and you'd be right. But you're supposed to also have learned at some point in this course that the limit as x approaches infinity, 1 over x to the n, where n is greater than or equal to 1, this always goes to 0. Now, let me make a graph of that real quick so that you can try to believe what I just said here. So if we look at the graph of 1 over x to the power of 1, let's make that, let me actually just make that to the power of n. We'll let n equal 1. As x goes to infinity, as you go to the right here, see how this number approaches 0? Hopefully you can see that.
Yeah.
Okay, and if I make n 2, if I make it 3, if I make it 4, 5, 6, doesn't really matter. It's always approaching 0. And that's key here. So let's go back to the actual problem here. So what that means, and I'm gonna do this in a different color here. I'll do it in blue. It means that 2 over x goes to 0 because 2 times 0 is 0. 3 over x goes to 0, and 1 over x squared goes to 0. And that's all because of this up here.
When n is greater or equal to 1.
Yes.
So yeah, that.
So that's
okay.
1, that's 2.
And even with the x squared, it's still 0. Okay.
Yes. X cubed, x to anything. Yeah. X to the 1.5 power, even that goes to 0. So what are you left with? Well, you can't plug in infinity, so that's kind of an exception to what we said earlier. You just see what is left over. Well, what's left over is 7/4.
Hmm.
Okay, now in a previous math class, you learned to look at the ratio of the leading coefficients, and that works most of the time, but not all the time.
Mm-hmm.
But that is your final answer.
Okay.
All right, so I'm going to snip in the next one here. Okay, so question A wants the limit as x approaches 5. So this is a piecewise graph, and there's what's called a left limit and a right limit. So the number that goes here really is based on the following. It's the limit as x approaches 5 from the left. So that's not a negative sign. That means from the left. Okay, and you want to use the one that's left of 5. That function
Because,
that's,
sorry, you're saying from the left because it's x is less than 5.
yes.
Okay.
So we first want to use the one that's from the left, and that is this function here. So it's x minus 1. So you just put that number in, so it's 5 minus 1, which is 4. That's good. Then we want to find the limit as x approaches 5 from the right. So this right here means from the right.
What is that, a little star thing?
It's a plus.
Oh, sorry.
It's a really bad
Okay.
plus.
Oh, you're fine. You're fine.
So let's make it better, plus.
Okay.
And then you want to use the one that's greater than 5, which is this one right here. It's just 4. The function is just 4. And these are the same, which is what you want. So the answer is 4.
Hmm. Okay, kind of lost me a little bit on that one, but how come you're not?
So let me show it graphically, because that will make more sense.
Okay.
And that you know, the picture really helps here. So let me go back and new share. And this is actually useful because you may want to graph piecewise functions. So you have to use a curly brace, and then you type in x less than 5, and then 4 is good from 5 less than or equal to x less than or equal to 6, and then x plus 2 is good for x greater than 6. All right, so we want the limit as x approaches 5. So let me just put a dot there just so we can sort of see what's going on. So we want the limit as x approaches this point right here. This is x equals 5, where my mouse cursor is.
Mhm.
So we look from the left. From the left, what is the y value that it approaches? And it approaches the y value of 4.
Mm-hmm.
From the right, it also approaches 4. They have to approach the same thing.
Oh, okay.
Okay, so that's why for part A, the limit is given as 4.
Okay.
All right, now for part B, you can see on your screen, it's or on your paper that it's the limit as x approaches, is it 6? Let me go back, 6, right? And that's different. There, if from the left, it approaches this point right here, 6, 4. But from the right, it approaches the point 6, 8. Do you see how they're not the same y value? There's what's called a jump between them.
Mm-hmm.
So it's discontinuous, and the limit does not exist because they don't approach the same value. From the left, which is again a little odd, but you actually just trace your cursor from the left, it approaches this value of 4. From the right, it approaches, you know, this other value, 6.
Okay. Okay.
So in terms of like the answer, and I've got a decent, I think it's a decent analogy here, but let me go back to the other screen. The limit here for part B is for 6 is that it does not exist. So it's the letter B.
Okay.
In that. Okay. So the analogy I make, and I hope this is a decent one, but it's like this. There's a river, and you approach the river from this path right here, and I approach the river from this path right here, and there's a bridge, and everyone's happy. Okay, this is your nice, smooth, continuous function. Okay, but here's the more common situation. Here's the first type of situation. So we've got our river, and you take a path, and I take a path, but there's no bridge. Okay, there's no bridge here. The limit exists though. The limit exists because we can see each other. You're there and I'm here, and we can see each other. Okay, we just because we're at the same place, we just can't cross because there's a gap or what's called a hole in math.
Okay.
Okay, so the limit here exists because we're right there. We're okay, right? And then if I keep going with this reference here, the one that we're kind of looking at in this other problem is you're there, and I'm down here, and imagine there's trees and stuff in the way, like we can't see each other anymore because there's a gap between us. And it doesn't matter whether the bridge is there or the bridge is there, which is that point. We are not at the same place anymore.
Okay.
And that's what I'm trying to convey in that graph. Like there's a jump between them. In that case,
Right.
we need a boat to get between us to get there.
Okay.
There's
Right.
obviously good.
So you're just saying like this, the limit is when there's that hole.
Yes.
Okay. Okay.
So if there's a hole, it's okay because you're still approaching the same value. Like, and that's what I was trying to show you. Like up here, it's like, yeah, I can see you. Hey, how's it going, kind of thing. But we can't actually connect because there's a gap between us. And here, whether there's a bridge or not, we're so far away because it's vertical or down the stream, we can't. We're discontinuous.
Yeah.
There's no way to connect them. We can't, move the stream or anything.
Okay. Yep.
Okay. Now the nice thing is we might be done with limits. We'll see here. I don't know. They don't come back in the course. That's what I try to tell students that are taking this, especially in high school. They really struggle with this concept, and it's a hard one, but it doesn't come back again in the course. Okay, so square root functions, the square root of x, it has this graph that starts at 0 and it goes like that forever. And to determine where it is continuous is actually really asking what is its domain. So to find its domain, you set this inside part, 6x minus 7 greater than or equal to 0. So to solve this, you add 7 to both sides, divide by 6, and you get x is greater than or equal to 7 over 6. Continuous, though, requires that, I think, I'm sort of guessing here, I believe it wants what's called the open interval. And so at the leftmost point of this graph, it's neither continuous or discontinuous because there has to be a value from the left and the right. So on a number line here, like normally we would say, okay, that's 7/6. That's everything to the right. It's bracket 7/6 comma infinity. But I believe because of the way that this is set up, that it wants what's called the open interval. So it's just 7 over 6 to infinity. And this is one of those like Pearson things where, if we looked at the homework, we would know for sure whether it wanted the open or the closed interval, but pretty sure 7 over 6 is good.
Yeah, all it says under it is to simplify your answer and type answer in interval notation.
Yes.
Okay. Okay.
All right, so let me move on here to the next question. Okay, so they give you this graph, and then they give you 3 graphs to choose from. I'm going to go ahead and go over to Desmos and graph this thing just to get some more practice on that,
Mm-hmm.
and that also give us more information. You can do it by hand, but I don't. It would take us a while maybe to explain all that. So let's do it this way as a.
So,
Go ahead.
sorry, just for you, just to pause really quick, how you enter the 11 if x is less than -1 is with those fancy brackets.
Curly braces, yeah. So
Yeah.
they are. I'm doing it from the keyboard, but it's all here, I think. And like anything else, if you just aren't sure, you Google search whatever you're
Mm-hmm.
trying to do. But yeah,
Yeah.
less than or equal to x, less than or equal to 3, and then 11 if x is greater than 3. All right, so this picture isn't great. I'll hit the home button here, see if we can get a little better. Yeah, there we go. So this I think is and then the question is, well, what's going on right there at the end? So if you hold your mouse down and you get right to the end point, you see undefined, it actually shows you a hole. Whereas if you don't hover over it, you don't know. So that's why it's good to check there. And then this one is good right at the end point there. So in terms of like which graph it is, it looks like it's graph A.
Mm-hmm. Okay.
Now to answer
Gotcha.
part B, it says, where is the function discontinuous? So continuity, think of it as like, are there any jumps or breaks? And clearly there's a break here at -1. So the discontinuity x value is -1 for sure.
Okay.
Now you keep going, keep traversing this curve, and you get up to this point right here. This is called a corner. And this corner is awkward, but it's continuous. Like they both even though it's undefined there, actually. Oh, I'm sorry. It's undefined. But there's an overlap there. So because they touch right there at 311,
Mm-hmm.
you're okay. So it's continuous there. I know it says undefined here, but that's because of I'm looking at it from the red's perspective, from this third one's, not from the black. The black line covers up that like place where they come together. It takes precedence.
Okay.
So that is part B is just x equals -1, and then part C. So part C says find the limit from the left and from the right from any values of x found in part B. So we're supposed to go to our graph, and we're supposed to say, okay, from the left. So see, I'm traversing it from the left.
Mm-hmm.
What is the y value that it approaches? And even though it's undefined there, it's still approaching a y value. That y value is 11. So from the left, it's 11.
Okay.
And then from the right, and you can go as far right as you want. You can even go all the way over here, but you got to get back to where x is -1, and the y value there is 3. And if it wasn't defined, you would still use the y value for it. Okay, so let me go back to this other screen so you can see that's part C where it's asking for the limit from the left, 11, limit from the right, 3.
Okay, awesome.
Any questions on this?
18. So halfway through.
Halfway through. All right. Find the average rate of change of the function over the given interval. Just make sure you're still seeing the screen here with the okay. I had some issues the last few days where I forgot to share my screen. It was not good. Okay, the formula here for average rate of change, they call this They call this a rock. You might have even seen it. It's f of b minus f of a over b minus a, and they have to give you an a and a b. The a is the first value, the b is the second value. So when you put those numbers into this formula, it's f of 2 minus f of 1 over 2 minus 1. So this is the correct answer here.
Okay.
Now, in terms of like the next box, we have to actually do some work. Okay.
Mhm.
So we have to actually find each of these. So f of 2 means to put 2 in for x in this function. So it's square root of 3 times 2 minus 2, which is square root of 4, which is 2. And we do the same thing for 1. 3 times 1 minus 1, I'm sorry, minus 2. 3 times 1 is 3, minus 2 is 1. Square root of 1 is 1. So that's the numerator. Okay, so we go back, we put those values in the numerator. 2 minus 1 over 2 minus 1. It ends up equaling just 1.
Okay, so you take that equation.
Yes, you have to know this equation, and then they have to give you the a and the b,
Mhm.
and then you write the equation, but then you go back and find the numbers that go in there.
Okay. Okay. All right.
Okay, actually, so we get to do another one here. This one's really similar. All right, so average rate of change, this is your 0 is your A, 7 is your B, so it's f of B minus f of A over B minus A. Your B is 7, so f of 7 minus f of 0 over 7 minus 0. And that's again because it's average rate of change, a rock, average rate of change. So we go find f of 7, we calculate it, it's square root of 5 times 7 plus 1, which is the square root of 36, which is 6. And then f of 0, square root of 5 times 0 plus 1, square root of 1, which is 1. So in terms of our numbers here, f of 7 is 6, f of 0 is 1 over 7 minus 0. So it's 5 over 7 is your final answer.
Okay, that makes more sense.
Yes.
That was, yeah, I think I just need to see it another time.
Yes. If you've taken any college algebra or you took some math in high school, which we all
Yeah.
did, you did this. You probably didn't understand what it is that you were doing, which is sadly the case in a lot of these cases. But it's really just getting some numbers, putting them into the formula, and moving ahead.
That's what I'm better at.
Yeah. The calculations.
Yeah.
All right. All right, suppose the position of an object moving in a straight line is given by s of t equals 3t squared minus 7t minus 7. Find the instantaneous velocity at time t equals 3. All right, so how do we want to do this? So think of, how do I do this? So this is the kind of the heart of this whole limiting stuff, and I probably owe you a short explanation of this. So let's say there's a curve that looks like this, and this is A. Actually, let me do it differently. So this is A, and this is B. This is f of A, and this is f of B. So when we do that, f of B minus f of A over B minus A, believe it or not, it is just the slope between these 2 points.
Okay.
And the slope between those 2 points looks something like that. Okay, there's some slope between there. Great. Now, calculus does the following. It makes B infinitely close to A.
Okay.
And what that means is like think of like if you've ever seen a hotel, they have like room numbers like 100 to one, or the room 100 and room 101.
Mm-hmm.
And you can sort of get like you can get right in the middle between those two rooms.
Mm-hmm.
And then you can get right in the middle of those, and then you can get right in the middle of those, and right in the middle of those, and you can keep getting closer and closer and closer. And if you were small enough, you could just keep, down to the micro level, get
Mm-hmm.
smaller and smaller and smaller. So calculus is about this B being so close to A that it is essentially at A. Like you're essentially right on top there.
Okay.
So this red line is what's called a secant line. And if you remember from geometry, a secant line cuts through a circle at two places.
Mm-hmm.
Well, the tangent line to a circle touches it in one place.
Oh,
And that's
right.
what we're doing here. We're progressing from hitting it in two places to figuring it out at one place.
Okay.
And that's about the best I can do in like a 2-minute explanation of it. I mean,
Sure.
there's more that can be done, but in terms of like this problem here, I'm going to give you, I just want to give you the answer to this because it's easier to explain from the answer than from trying to justify it. So what they're saying is B is approaching 3. So imagine that B is like 3.000000001. Okay.
Mm.
All right. So you're evaluating the function like right next to, and think of A now. A now is really 3.
Mm-hmm.
And B is like right next to it, but just tiny bit away from it, just the
Mm-hmm.
tiniest little bit. So you're evaluating the function at that point, just a little bit away from it. Then you're evaluating it at 3, and then you're subtracting that little bit of difference between the two of them.
Yeah.
So in terms of like how you actually get the number here, which is what you care about, is you literally do you literally set B equal to, and you don't have to go out that far. We'll go out like 3.0001, and then we're going to set A to 3, and we do this calculation. We do f of B. Well, let's just f of B minus f of A over B minus A, and we use it with this function up here at the top.
Okay.
So in terms of how we actually do that, I'm going to go back to this other calculator. If I can find it. There we go. All right. So we're going to let B equal 3.0001. And then we're going to go 3B squared. Why didn't it do all that? 3B squared minus 7B minus 7. Why are you doing this? All right, so there's that number, and then we're going to do A equals 3. And we'll do the same thing, except we'll change these. Okay. And then, so now we're going to do what the calculation I just mentioned, this f of B minus f of A over B minus A. Okay, but instead of f of B, I'm going to put in that decimal there. See if I can grab that. And instead of f of A, I'm going to use the -1. And you can see that it's basically 11,
Mm-hmm.
which is yeah, that is correct. So you basically 11 for that. All right, so let's go back to the other screen here. Okay, so what question are we up to? I'm sorry again.
We're on 13.
13.
Yeah.
Okay. Yeah, so I need just a short break. I don't want to restart the Zoom, so it's okay if we just
Take a break. Yeah.
yeah, till right at 2 o'clock and start back. Does that work for you?
Sure. Yep. Absolutely.
I'm gonna mute myself. You're welcome. You can either leave the room and come back in or stay in the room. It's up to you, but I'll be back in about 10 minutes.
Okay. Sounds good.
Thank you.
Mhm.
All right, Olivia, I'm back. Let me know when you're ready.
Ready.
Excellent. Okay, so we're going to keep going here and see what we can get done. All right, so the next question is to find the instantaneous rate of change, blah, blah, blah. Okay, so we're moving into derivatives. We're out of limits and we're moving into derivatives. And let me just make sure you're seeing my screen here. One I think you should be seeing. Okay,
Mhm.
so find the instantaneous rate of change to the function at the given point. So we're gonna here's our first derivative rule. We're gonna have a bunch of these that are part of this course. So if they give you x to the n, if your function y or f of x is x to the n, the derivative, which is this little prime symbol here, you bring the exponent down and you subtract 1 from the exponent. So we're going to apply that to this problem here. So you're going to take the derivative of this, and you can see you bring the 2 down in front of the x, and then you subtract 1 from the exponent. You do
Okay.
the same thing for this 5x. The exponent is 1, so you bring a 1 down, and then you subtract 1 from it, and then you simplify. So this becomes 2x to the power of 1 plus 5. And then you put that value of 0 in for x. So you're actually finding f prime of 0, which is 2 times 0 plus 5, which is just 5.
Okay. Okay. Cool.
So this is the shortcut.
Mhm.
And we'll see hopefully the next, yeah, yes. Okay, so we are there, just making sure.
Mhm.
So it's good. There's in the classroom, they teach you this sort of longer way to do it. To start, we're kind of cutting through that a little bit. And we'll go on here. So this is yet another power rule problem. So the derivative, whenever you have x to a power, you bring that number down in front. So that negative stays, you bring that 2 down, x, and then you subtract 1 from the exponent.
Okay.
Plus 2, the exponent is 1, so you bring that 1 down, x, and then you subtract 1 from the exponent. Now this last one is a new derivative rule.
Mhm.
If your y is what's called a constant, or your f of x is a constant, the derivative of a constant is always 0. So the derivative of -3 or minus the derivative of 3 is 0.
Hmm.
So we've got 2 derivative rules now. We have what's called the power rule. This is called the power rule. And then we have just the derivative of a constant. So a couple things to remember there. So to simplify this, it's minus 2x power 1 plus 2. And that's your answer to part A, or the first part of this.
Okay.
The next part, actually not that difficult at all. You're just evaluating the derivative. You're just taking the value of x that they give you. Like for the first one, x is 1, and they're saying put 1 into the derivative. So it's
Mhm.
minus 2 times 1 plus 2, which is 0.
Okay.
The next one says the same thing, put 2 in for x. Minus 2 times 2 plus 2 is minus 2. And then the last one here, same thing. Minus 2 times 3 plus 2 is minus 4.
So what would the answer look like if the derivative does not exist?
We won't see that for a bit
Oh, okay.
at a point, but it's gonna be like division by 0 or something, or square root of
Okay.
yeah, these are problems are generated by software, and they probably just put those boxes, those extra boxes in anyway.
Okay.
All right, so the next one here is a graph. So one thing that would definitely help me for future lessons is to increase the size of the graph. You'll see there's the magnifying glass on
Yeah,
there.
you want me to send that to you right now?
No, I don't need it for this one. I
Okay.
may not ever need it, but that is potentially an issue. So
Sure.
there are 2 types of okay, so there's a couple of different places where the derivative does not exist. So one is a discontinuity. And a discontinuity is a hole or an asymptote or a jump. Okay, but that's not the case here. The other possibilities are what's called a corner, which I kind of alluded to. So corner looks like that, or what we see here, which is called a cusp. Cusp has that sort of shape to it. You can also see it going the other direction as well.
Okay.
And the derivative just does not exist there when x is 0. It's always the x values.
Okay. All right, so 0.
Any questions on that?
Not really.
Okay, so your question will be answered in this next problem. All right, so I alluded to this in the previous problem. It's where the function is maybe discontinuous. And probably the best path here is to actually graph this.
Okay.
So x squared minus 9, x plus 6. You can hit that home button to get a kind of a view that you're there, but sometimes you got to zoom out to actually see what's going on here.
Okay.
So the only place that's really an issue is here is that x equals minus 6, and you can see that's a vertical asymptote. So it's nice and smooth though everywhere else, nice and smooth, no cusp or corners. I mean, that it's just a rounded edge, a filleted edge there and there, filleted edge. We're looking for something like I mentioned, a jump, a hole, a vertical asymptote, a cusp, or a corner. And the only one that exists here is a vertical asymptote at minus 6. So that's the only place where it is not differentiable.
Okay.
All right, so let's go back to the other screen. All right, so the next question says to graph the derivative. This is actually a really good exercise for students. They're very visual, especially if you're at a classroom or even a lab, because there's also a nice there's a set of steps here. So the first thing you do is you identify horizontal asymptotes, and those could be mins, they could be maxes, or just where, like right here, this is a horizontal asymptote right here.
Okay.
Okay. And what you do is the way I like doing is actually you draw a graph right below it and you put that place right on the axis. And the reason is because wherever there's a horizontal tangent like this, the slope is 0. And that's the whole idea here. The derivative is the slope. All right, and it's exactly
Okay.
0 right there. And that breaks up your original function into windows or regions. Okay, now notice on the left here, the left side here, we'll say, I guess I'll just write in here, the graph is increasing. It's increasing because it's going up and to the right. Do you agree that the tangent lines look kind of like this along this graph here? Do you see I'm just sort of trying to touch it at one point?
Mm-hmm.
All of those have positive slope. And
Yeah.
since the derivative is the slope, the derivative is in this case, it's a graph of the slope. All of those slopes are positive, so it looks something like this. Now, if we do the same thing over here on the right and we start drawing tangent lines, all the tangent lines have positive slope. They're all going up and to the right. So this is also increasing up and to the right. And so the derivative, graph of the derivative, the graph of the slopes is also increasing. So you're looking for a graph that looks like this.
Okay.
All right, so the next question, kind of the same deal here. There's a couple of shortcuts to doing this that I think are probably worth mentioning. So we looked at, and let me just come off to the side here. So we looked at this earlier. I said y equals x squared, and I said its derivative, you bring the exponent down. So it's 2x, 2 minus 1, you subtract 1, which is 2x. The original function is a quadratic, and its derivative is linear. So if we were to graph these on the same graph, there's the quadratic, there's the linear, okay, and this follows a pattern. So the quadratic has like a turning point here. It goes down and goes up. That's called a turning point. You see this in cubic graphs a little bit more. Let me draw one of those here. So a nice cubic graph that looks like this, it has two turning points like that. Okay, and that's a cubic. Well, its derivative is 3x squared. It's a quadratic. So I'm trying to get you to buy into here is that the derivative is always 1 degree less. So it's going to have one less turning point.
Yeah.
So if you look at your graph, this one right here has two turning points.
Mm-hmm.
Y1 has two turning points, so you can think of it as maybe a cubic, but Y2 only has the one turning point. It looks like it's a quadratic. So Y1 is the original, and Y2 is the derivative.
Right. Okay.
Okay, and I'm trying to base that on sort of this like more generalized approach than to just do this graphing stuff that we did in the last problem.
Mm-hmm.
So the in terms of answer here, I guess Y1 is looks like it's letter A.
Okay. Okay.
Is that everything?
It should be.
Okay. How do you let me just stop the recording here.